Welcome. Let the world feel a little less solid tonight, because we are about to step into the place where certainty softens and reality begins to hesitate. The room feels unusually still tonight, perhaps because you are already deep inside the quiet hours, or perhaps because of what we are about to discuss, the strange, shimmering texture of reality that exists just beneath the surface of the obvious. We often assume the world is a solid, definite place, a great clockwork mechanism of cause and effect, where every object has a clear location and a determined speed. We live our lives based on this comfortable, classical intuition, feeling the gravity holding us to the planet, watching the pendulum swing with predictable certainty, and relying on objects to be exactly where we left them. Yet, if we lean in just a little closer, if we turn down the bright lights of our common sense, we find that the foundations of all that is visible are built not on certainty, but on a kind of elegant, eternal hesitation. This subtle, mathematical tremor at the core of existence is not a philosophical idea. It is a fact, repeatedly confirmed by painstaking, quiet work in laboratories across the past 100 years. Picture the electron, a tiny, fundamental speck of charge. Meticulous experiments have shown that this electron refuses to simply be a particle. When unobserved, it exists as a dispersed cloud of pure potential, a mathematical ripple covering a vast area. It is everywhere and nowhere at the same time, behaving like a wave, until the moment an apparatus attempts to measure it. Quietly, the universe insists on this contradiction. Only in the presence of an observer, of some interaction, does that diffuse potential collapse instantly into a single, definite point. This is the central paradox, the impossibility stack that sits at the very heart of the modern scientific endeavor. How can something be both wave and particle, both a dispersed probability and a definite reality, until the act of observation forces it to choose? The implications are astonishing. If the fundamental building blocks of the chair you are sitting on, the air you are breathing, and the light that illuminates your surroundings do not possess intrinsic properties until they are measured, then where did their certainty go? What if our perception, our mere focused attention, is not just a passive witness to reality, but an active participant in its quiet completion? The ancient philosophical traditions of the East have long hinted that the world of definite forms is a grand illusion, a veil woven from perception and the quiet consent of consciousness. Now, experimental physics, working with the coldest instruments and the purest mathematics, has arrived at a strikingly similar conclusion, finding echoes in those mythic patterns of duality and cycles. This realization forces a gentle, profound shift in our relationship to the world. It means that the objective reality we cherished might be merely the stable, predictable shadow of a much deeper, more fluid structure. Imagine watching a single particle hesitate at the crossroads of existence. Take a slow, deep breath and notice how the room feels, how your consciousness inhabits this moment. Leave a comment telling me what time it is and where you are listening from tonight. We are about to begin a long, slow journey inward, past the surface of things, into the very language of existence. But what if certainty was never part of the design? To understand this behavior, this essential hesitation, we must go further inward, and that journey begins with the strange geometry of light itself. The journey into the secrets of the subatomic structure must necessarily begin with light, the messenger that brings all information to us, and yet whose behavior is the very first piece of evidence that the classical worldview is incomplete. The photon, the fundamental quantum of light, is a curious traveler. We are taught in our schooling that light is an electromagnetic wave, a ripple in the fabric of the electric and magnetic fields, sweeping across the vast expanse of the cosmos. This model explains a great deal: the color of a sunset, the refraction of light through a prism, and the vast, slow curve of a radio signal across 100 kilometers. But as the 19th century faded into the 20th, meticulously careful measurements began to yield a quiet series of anomalies, tiny, persistent whispers that light was not only a wave, but also something profoundly different, something discrete and particulate. You notice that the concept of light starts to stretch and thin, unable to hold its shape under the pressure of new evidence. The problem first showed its subtle face in the mystery of the blackbody radiator, the perfectly idealized object that absorbs all incident radiation. Scientists attempted to model the energy distribution of the light emitted by a heated blackbody, and their calculations, based on the reliable, flowing mathematics of continuous waves, led to a preposterous conclusion. They predicted that the energy emitted would tend towards infinity at the shortest wavelengths, a catastrophic, nonsensical result they dryly termed the ultraviolet catastrophe. The mathematics of the classical worldview, the very mathematics that had predicted the orbits of the planets and the trajectory of a cannonball, utterly failed when attempting to describe the simple, steady glow of a hot object. The theoretical reality should have filled the entire universe with infinite energy, a kind of cosmic white noise, and yet the experimental reality was calm, definite, and measurable, a profound anomaly that demonstrated the limit of what we thought we knew. It was Max Planck, working with a quiet desperation at the turn of the century, who introduced the simplest, most revolutionary fix. He did not initially believe his own idea, treating it more as a mathematical trick, a temporary scaffolding to hold up the failing classical structure. He proposed that energy was not continuous. Instead, it could only be absorbed or emitted in tiny, indivisible packets, which he called quanta. This concept was like saying that water could not flow like a stream, but could only be delivered in small, pre-packaged cups, each containing a fixed, minimal amount. The energy of each quantum was directly proportional to the frequency of the light, scaled by a new, mysterious constant, now known as Planck's constant, or H. He found that by making this quiet, mathematical compromise, the ultraviolet catastrophe vanished entirely. The universe suddenly had a discrete, grainy texture to its energy, and the constant H became the fundamental speed limit on certainty itself, the smallest coin in the cosmic treasury. We begin to see that the universe prefers to count its energy rather than pour it. But the true genius of Planck's scaffolding was revealed by Albert Einstein a few years later, in his explanation of the photoelectric effect, a second experimental anomaly that confounded the wave-based model of light. When light shines on a metal surface, it can eject electrons, a phenomenon utilized today in countless pieces of technology, from solar panels to digital cameras. According to the wave model, the energy transferred to the electrons should depend on the intensity of the light. The brighter the light, the more energetic the electrons. Yet, the experimental results were stubbornly different. The number of ejected electrons depended on the intensity, but their maximum kinetic energy depended only on the frequency or color of the light. A dim blue light would eject very fast electrons, while a brilliant red light, no matter how intense, might eject none at all. This was an absolute contradiction of the wave theory, which held that energy was spread out and accumulated over time. Einstein looked at Planck's quanta and recognized their deep reality. He proposed that light itself was composed of these tiny, localized packets of energy, which he termed photons. When a photon hits the metal, it acts like a miniature particle colliding with an electron, giving its entire quantum of energy to the electron in a single moment. Blue light has a higher frequency than red light, and thus, according to Planck's relationship, each blue light photon carries a greater, more concentrated packet of energy. This explains the anomaly perfectly. The energy of the electron is dictated not by the overall brightness of the wave, but by the individual energy carried by the single, particulate photon it collides with. The intensity of the light is simply the rate at which these photons are arriving. A gentle stream of high-energy packets does far more work than a torrent of low-energy packets. This presented the science world with the first great mystery of the new physics, the one that would haunt every subsequent development. Light behaves like a wave when we consider its propagation, its interference, and its refraction. But light behaves like a particle, a distinct quantum object, when we consider its interaction with matter, such as in the photoelectric effect. It seems to have a dual identity, a quiet, conceptual split personality. When we ask light to show us its wave-like nature, it complies beautifully. When we design an experiment to confirm its particulate nature, it is equally cooperative. It never displays both faces at the same time. The choice seems to be made only when a specific question is asked of it. This wave-particle duality is the essential hesitation mentioned in the introduction. The photon travels across the cosmos as a diffused wave of probability, a potential that fills the entire intervening space. And then, at the very moment it interacts with an atom or a detector, it collapses into a discrete particle, a small splash of concentrated energy at a single point. It is as if the universe is running an endless, internal calculation, leaving the photon in a state of conceptual superposition, a blend of possibility, until an observation forces a definitive answer. The act of measurement leaves a profound, particulate fingerprint on the fluid geometry of the photon's life. We find ourselves looking through the window of the laboratory at a universe that seems to be in a constant, quiet conversation with itself, deciding its next move only at the last possible moment. The certainty of the classical world fades into the poetry of statistics and probability, but this was only the beginning of the quiet unraveling. To truly appreciate the scale of this dual identity, we must turn our attention away from the photon and look at matter itself, asking the impertinent question: if light can be a particle, can a particle also be a wave? And that is the question that takes us into the next stage of our journey. The quiet revolution initiated by Planck and Einstein, demonstrating that light could behave as both a wave and a particle, left the world of physics in a state of carefully contained tension. For centuries, the distinction between matter and energy, between the solid world of objects and the ethereal realm of light and heat, had been absolute. Now, that boundary had become porous, shattered by the discrete mathematical whisper of the photon, but the tension remained asymmetrical. Only energy had been granted this duality. Matter, the electron, the proton, the atoms that compose you, and everything around you was still assumed to be solid, definite, and purely particulate. It possessed mass, it occupied space, and it behaved with the reliable certainty of tiny billiard balls. It was a firm anchor in the sea of conceptual uncertainty. This intellectual imbalance, this nagging lack of symmetry, began to quietly trouble the imagination of a young French aristocrat and physicist named Louis de Broglie. De Broglie was not working in the noisy, competitive laboratories of the time, but in the contemplative silence of his own philosophical inquiry. He felt that the universe must possess a deeper, more profound elegance than current physics allowed. If nature, at its most fundamental level, was truly unified, then why should matter be restricted to the definite realm of particles, while light enjoyed the freedom of waves? You begin to appreciate the deep, philosophical yearning for symmetry that drives scientific discovery. In a move of audacious simplicity, de Broglie proposed in his 1924 doctoral thesis that this duality must be universal. He suggested that if waves of energy could exhibit particle-like characteristics, then particles of matter should, conversely, exhibit wave-like characteristics. He proposed that every single object in the universe, from the largest galaxy to the smallest electron, has an associated wavelength, a mathematical ripple that governs its motion and behavior. The sheer scale of this idea, the notion that you yourself possess a wavelength, is quietly astonishing. He was able to calculate this wavelength using a beautifully elegant and simple equation that linked the particle's momentum, a measure of its mass and velocity, to Planck's constant, the same fundamental number that governs the energy of a photon. The equation states that the wavelength is equal to Planck's constant divided by the momentum. This connection meant that the wave-like nature of matter is inversely proportional to its momentum. For massive, fast-moving objects, like a baseball thrown across a field or a passenger train moving at 100 miles per hour, their momentum is enormous, and thus their associated wavelength is incredibly tiny, far smaller than the smallest detectable dimension. This is why we never observe the wave nature of macroscopic objects. Their wavelengths are so minutely small that they are utterly beneath the threshold of our perception and our instruments. For all intents and purposes, a thrown baseball is perfectly particulate. But when we turn our attention to the subatomic world, to the electron, a particle with almost unimaginably little mass, the momentum drops dramatically. Consequently, the de Broglie wavelength for the electron becomes large enough to be experimentally detectable. De Broglie was not proposing a new kind of wave, like a sound wave or an ocean wave. He was proposing a matter wave, a wave of pure probability that describes where the particle is most likely to be found. This was a profound conceptual leap. The wave is not the substance itself, but the mathematical ghost that guides the substance. The scientific community, however, treated de Broglie's proposal with quiet skepticism. It was elegant, certainly, but it lacked any direct experimental evidence. It was an idea born purely from a philosophical desire for symmetry. That evidence arrived a few years later in one of the most significant experimental anomalies in the history of science, conducted by Clinton Davison and Lester Germer at the Bell Telephone Laboratories, and independently by George Paget Thompson in Scotland. Davison and Germer were actually studying the surface of nickel crystals using a beam of electrons, looking for entirely different effects. During one experiment, a laboratory accident caused their nickel target to become heavily oxidized and then subsequently heated in a vacuum, causing the numerous tiny crystals of nickel to fuse into a single, large crystal. When they resumed their experiment, they observed an utterly unexpected result. Instead of the electrons scattering randomly in all directions, as one would expect from particulate collision, the electron beams scattered off the nickel surface only at specific angles, forming a distinct, sharp pattern. This pattern was immediately recognizable to physicists. It was the classic diffraction pattern that only occurs when waves, and not particles, pass through a regularly spaced grating, such as a crystal lattice. Diffraction is the phenomenon where waves spread out and interfere with one another, creating alternating bands of high and low intensity. The experimental results suggested that the stream of particulate electrons had somehow diffracted off the crystal lattice, meaning the electrons were behaving like waves, guided by their associated de Broglie wavelength. They had stumbled upon the third great experimental anomaly. Matter, once thought to be exclusively particulate, clearly exhibited wave-like behavior. George Paget Thomson, working independently, confirmed this result by firing an electron beam through a thin film of metal, producing the exact same bullseye diffraction rings that X-rays, which are known waves, produce. The irony of history is quietly profound here. J. Thomson had won the Nobel Prize for proving the electron was a particle. His son, George P. Thomson, won the Nobel Prize for proving that the electron was a wave. Father and son had bracketed the entire conceptual shift from classical certainty to quantum probability, a lovely demonstration of continuity and contradiction. This experimental confirmation provided the final piece of the puzzle. The duality was complete. Light is both wave and particle. Matter is both particle and wave. Every single entity in the universe possesses this twin nature. The consequences of this discovery are impossible to overstate. It means the electron traveling around an atom is not simply a tiny definite planet orbiting a central sun, as the early models suggested. Instead, it is a standing wave wrapped around the nucleus, a steady, mathematical vibration, a resonance. The electron's wave-like nature is what determines the stable, discrete energy levels of the atom, explaining why atoms do not simply collapse and why the entire edifice of chemistry and biology is stable. The electron wave will only fit perfectly around the nucleus at certain specific wavelengths, resulting in only certain specific energy levels being allowed, just as a vibrating string on a musical instrument can only produce certain standing waves that correspond to definite musical notes. The atom is not a mechanical clockwork. It is a musical structure, a quiet composition of standing probability waves. We are beginning to see that the deeper structure of reality is based on harmony and resonance, a subtle, beautiful pattern rather than raw mechanics. This leads us to the critical conceptual question. If everything is a wave of probability until measured, what exactly is the nature of this wave? It is not a disturbance in space like an ocean wave carrying water. It is a mathematical potential, an expression of our incomplete knowledge, and the ultimate determinant of what the particle might do. To understand this strange, non-physical wave, we must turn our attention to the mathematical description of the wave itself, the equation that governs the flow of this probability. This equation is the engine of the quantum world, the rulebook for the universe's elegant hesitation, and its implications are the very definition of the deeper structure. And yet, even then, this new mathematical language carried within it the seeds of even greater contradictions. But this was only the beginning. With the experimental confirmation of matter waves, the next logical step in this quiet, conceptual journey was to find the mathematical rule that governs them. If the electron is guided by a wave of probability, then science needed the score, the sheet music for that subtle vibration. This profound task was taken up by the Austrian physicist Erwin Schrödinger, who in the year 1926 produced what is now the central equation of non-relativistic quantum mechanics, the Schrödinger wave equation. This equation is not simple to look at, filled as it is with partial derivatives and imaginary numbers, but its conceptual meaning is the key to unlocking the true strangeness of quantum reality. You can almost hear the quiet hum of 1,000 physicists solving this complex mathematical puzzle on their chalkboards. The core element of this equation is the $psi, $psi, the Greek letter that represents the wave function of a particle. The wave function is not a physical wave that you could see or feel. It is a mathematical abstraction, a map of all possibilities. When Schrödinger first formulated his equation, he initially believed the wave function represented some kind of physical charge density, a continuous, smeared-out substance. He hoped that the wave equation would finally rid physics of the confusing, discrete nature of particles, returning to a purely wave-based world. But the interpretation of $psi quickly fell to a deep philosophical debate, solved by the gentle, steady hand of Max Born, the brilliant theoretical physicist who would become the grandfather-in-law of the musician Olivia Newton-John. A small, delightful historical footnote linking the precision of physics to the poetry of pop culture. Max Born proposed that the wave function $psi had no direct physical meaning itself. Instead, it was the square of the wave function's absolute magnitude, $psi, $2, that was important. This squared value, he suggested, represented the probability density of finding the particle at a particular location in space. This was a radical, monumental shift in the entire philosophy of science, the fourth experimental anomaly, disguised as a mathematical interpretation. Under the classical, deterministic physics of Isaac Newton, if you knew the initial position and velocity of a particle, you could predict its future position with absolute certainty. The laws were causal, definite, and absolute. Born's interpretation, however, stated that all the Schrödinger equation could ever offer was a statistical probability. It could only map out the probability pools where the particle was most likely to be found if a measurement were made. Imagine holding a handful of sand. The wave function $psi describes the shape of your hand and the kinetic energy of the sand, a beautiful, continuous description of potential. But $psi, $2, describes the likelihood that a single grain of sand will land on a particular square inch of the floor when you open your hand. The mathematics can give you the pattern of possibilities, but it cannot tell you the destiny of any single particle. Before measurement, the particle is mathematically distributed across all the locations where the wave function is non-zero. It exists in a state of superposition, a blend of all its possible states simultaneously. It is both here and there, and everywhere in between, not physically, but potentially. It is only at the moment of interaction, the measurement, that the entire wave function instantly and abruptly collapses, and the particle is found to exist at one definite location, and one definite location only. This concept of collapse is the great central difficulty of quantum mechanics, a deep philosophical wound that remains unhealed to this very day. The Schrödinger equation itself, which describes how the wave function evolves over time, is perfectly deterministic and continuous. It never contains the mechanism for abrupt collapse. It predicts that the wave of possibility should simply spread and diffuse forever, never resolving into a single point. And yet, the physical reality is that every time a scientist looks, the particle is definite, concrete, and singular. The mathematics suggests a ghost. The experiment finds a body. The implications for this collapse are profound for human reflection. It means that the objective reality we perceive is not the primary reality. The primary reality is the cloud of potential, the mathematical possibility described by psi dollar. Our observation, our intervention, acts as the conceptual trigger that forces the fluid potential to congeal into definite form. It suggests a participatory universe where consciousness, or at least the macroscopic act of measurement, is necessary to finalize the universe's internal calculation. The scientist is no longer an objective, detached viewer observing a pre-existing reality. The scientist is an active, if unwitting, participant in the creation of that reality. This links the new physics not just to ancient intuitions of illusion, but to the very nature of what it means to perceive. This is the great uncertainty principle at work, often mistakenly described as merely an observational problem. The true meaning, as developed by Werner Heisenberg, is far deeper. It states that there are pairs of quantities, like position and momentum, that are fundamentally linked, and the more precisely you know one, the less precisely you can ever know the other. It is not that our instruments are too clumsy to measure both perfectly. It is that the particle itself simply does not possess a definite, sharp value for both at the same time. If the particle is acting purely as a wave, its momentum is definite, but its position is utterly smeared out. If we force it to become a particle with a definite position through measurement, its momentum instantly becomes a diffuse blur of potential. This is a fundamental property of the quantum world. Certainty is conserved and never allowed to exceed a quiet, definite limit defined by Planck's constant. The wave function is the silent, mathematical evidence that reality is structured around potentiality, not actuality. It is the language of what could happen, not what must happen. And the transition from the probabilistic cloud to the definite particle, the moment of collapse, remains the great, unsolved question, the quiet threshold that separates the quantum world from our own. We can write the rules for the evolution of the wave, and we can calculate the probabilities of its collapse, but we cannot write the rule for the collapse itself. To understand this quiet, strange transition, we must now delve into the single most famous, yet most deceptively simple, experiment in the history of physics, the one that makes the wave function's behavior perfectly and unsettlingly clear. To understand this strange, non-physical wave, we must move on to a place where a particle's potential truly blossoms into contradiction. But this was only the beginning. The ideas of the wave function and the probability pools remain abstract until they are illuminated by the quiet, perfect genius of the double-slit experiment, an apparatus so simple in its structure, yet so profound in its implications, that the physicist Richard Feynman once called it the only mystery of quantum mechanics. Imagine, if you will, standing in a dark, silent chamber. Before you stands a flat wall containing two narrow, vertical openings, or slits, separated by a minuscule distance, like two quiet portals to the unknown. On the wall behind this barrier, A phosphorescent screen is placed to register the arrival of any particles that pass through. We begin by looking at the known world before this experiment entirely unravels it, asking what we would expect from classical intuition. If we fire a steady stream of miniature, particulate objects like tiny grains of sand or microscopic marbles at the barrier, what do we see on the screen behind it? The vast majority of particles will hit the wall, but those that make it through will pass cleanly through either the left slit or the right slit, landing directly behind the opening they traversed. Over time, as countless particles accumulate, we would see two distinct, bright bands on the screen, directly corresponding to the two slits. This is the behavior of definite, classical particles, an expected outcome governed by simple, definite trajectories and collision mechanics. Now, consider what happens if we fire a wave, say, a ripple on the surface of a perfectly still pool of water at the same two openings. When the wave encounters the slits, each slit acts as a new source of circular waves. These two new waves expand outward and overlap, and in the region of overlap, they interfere with one another. Where the crest of one wave meets the crest of the other, they add up, creating a region of constructive interference and maximum amplitude. Where a crest meets a trough, they cancel each other out, creating a region of destructive interference and zero amplitude. The pattern that develops on the screen is not two bands, but a series of alternating bright and dark lines, a signature interference pattern with the highest intensity occurring at the center, exactly halfway between the two slits. This pattern is the unmistakable signature of wave nature, born from the simple fact that the disturbance passed through both available paths simultaneously. The experiment now turns to the electron. The tiny particulate object that Louis de Broglie showed must also be a wave. We fire a beam of electrons at the double-slit apparatus. Initially, the expectation is that they will behave as particles and produce the two distinct bands. But when we look at the accumulation of millions of electron impacts on the screen, we find the unmistakable, quiet signature of the wave, the alternating bright and dark bands of the interference pattern. This is already a profound, unsettling result, a clear confirmation that electrons, which possess mass and charge, are fundamentally wave-like in their passage, spreading out and interfering with themselves as they travel through the two small openings. The experimental setup is then refined to its most philosophically challenging state. What if we send the electrons through, not in a steady stream, but one electron at a time, separated by a long gap of time, say, one single electron every 60 seconds. When the first electron hits the screen, it appears as a definite, tiny flash, a single particle impact at one point, just as you would expect from a marble. The second electron hits at a different, definite point. Over the first few minutes, the pattern looks random, like scattered shot, but as the number of impacts slowly grows, accumulating over hours, say, a period of 120 minutes, or 1,440 minutes for a long, slow accumulation, the interference pattern begins to subtly emerge, pixel by quiet pixel. This outcome is logically impossible under classical physics and represents the fifth great conceptual leap. For the interference pattern to emerge, the wave associated with the electron must have passed through both slits. But since the electron was sent through alone, it means the single, solitary electron's probability wave, $psi $, must have traveled through the left slit and the right slit simultaneously, interfering with its own potential path, before collapsing to a single point upon impact with the screen. It existed in a state of quiet, profound superposition, exploring all possibilities until the last possible moment. The particle, it seems, has no defined trajectory until its journey is over. But the story holds one final, exquisite twist: the quiet betrayal of the system. Scientists decided to simply watch the electrons. They placed a miniature detector, a tiny unblinking eye, near the two slits, designed to register which slit each individual electron passed through. The detector is a form of measurement, an interaction designed to force the electron to reveal its definite position. The moment this eye is turned on, the result on the final screen changes instantly and utterly. The interference pattern vanishes entirely, replaced by the simple, definite two-band pattern of classical particles. The electron, it seems, refuses to make eye contact. As long as it is unobserved, it remains a fluid, probabilistic wave, traveling both paths at once. The very moment we attempt to pin down its reality, to ask the definite question, "Which way did you go?" the wave function collapses. It is forced to abandon its ghostly, two-path superposition and commit to a single, definite reality, either the left slit or the right slit, behaving, once again, like a definite particle. The act of measuring the path destroys the wave-like property that allows for interference. The most subtle humor in this entire situation is that the experiment that proves the wave nature of matter is simultaneously the experiment that proves we can never observe that wave nature without destroying it. We can only catch a glimpse of the aftermath. This is the great, quiet implication for the human reflection. The universe does not seem to know its own mind until we ask a question. The physical reality of the electron, its defined position, is not an intrinsic property that existed prior to our measurement. It is an emergent property that arises from our interaction with its fluid potential. The electron is not hiding its path from us. It truly does not have a definite path until the measurement act forces a resolution. The quiet tension in the cosmos is the constant, subtle transition from the boundless potential described by the wave function to the definite actuality of our lived experience. This inherent, inescapable link between the observer and the observed is what defines the deeper structure, leading us to question the very meaning of separateness. If one particle's potential can instantly collapse across an apparatus, exploring multiple paths until a single resolution is chosen, what happens when two particles, born from the same quantum event, are linked together across vast distances? Does the act of observation on one particle instantly affect the state of the other, even if they are separated by 1 billion kilometers? This question, which tests the very boundaries of locality and information transfer, leads us directly into the concept of quantum entanglement. We must now turn our attention from a single particle's hesitation to the shared fate of two particles, to a phenomenon so strange that Albert Einstein himself called it spooky action at a distance. The deep, quiet consequence of the double-slit experiment is the realization that a single, isolated particle exists as a smeared-out potential until forced into definition. But the most profound conceptual difficulty arises when we consider two particles that are intrinsically linked, a phenomenon known as quantum entanglement. This is a bond so complete that the particles share the same wave function, a single, unified, mathematical description of both their possible states. The quantum bond is not merely a strong connection, it is a shared identity, a single object existing in two places, and its implications were so disturbing to Albert Einstein that they formed the basis of his most famous, quiet critique of quantum mechanics. Imagine two electrons, born from the same high-energy interaction. The total system must conserve a property called spin, an intrinsic angular momentum that electrons possess. For the pair, the total spin must be zero, meaning that if one electron is measured to have its spin pointing up, the other must instantly have its spin pointing down, and vice versa. Before any measurement is made, the wave function of the pair holds them both in a state of superposition. The first electron is simultaneously spin up and spin down, and the second electron is simultaneously spin down and spin up, an elegant four-fold probability blend. The shared potential exists, but the definite reality does not. Now, imagine these two entangled electrons are separated and sent off in opposite directions across an astronomical distance. Say, one travels to the distant star Polaris and the other remains here on Earth, separated by 500 light-years. According to quantum mechanics, even across this vast distance, their wave function remains perfectly unified, an invisible, intangible bond. The electrons themselves remain in superposition, simultaneously indefinite, until an experimenter on Earth decides to measure the spin of the local electron. The moment the Earth-bound experimenter measures the spin of their electron, forcing the wave function to collapse, a definitive state is chosen. Perhaps the electron is found to be spin-up. According to the quantum rules, the wave function of the entire system, including the particle 500 light-years away, instantly collapses as well. The distant electron at Polaris is instantaneously defined as spin down, even though no physical force or signal has traveled the great distance. The act of observation here on Earth has a non-local, quiet consequence for the distant companion particle. This is the spooky action at a distance that so troubled Einstein. His entire life's work was dedicated to the principle of locality, the idea that objects can only be influenced by their immediate surroundings, and that no influence can travel faster than the speed of light, which is approximately 300 million meters per second, a quiet cosmic speed limit. If the measurement on Earth instantly determines the state of the particle at Polaris, it seems as if information has traveled from Earth to Polaris faster than the speed of light, an apparent violation of the fundamental principle of special relativity. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, devised a famous thought experiment, the EPR paradox, intended to demonstrate the utter absurdity of this entanglement, the sixth great conceptual anomaly. The EPR paper did not deny the mathematics, it questioned the interpretation. They argued that the only way to reconcile the instantaneous correlation with locality was to propose that quantum mechanics was incomplete. They suggested that the electrons were not truly indefinite before measurement. Instead, they must have carried with them hidden variables, some unknown, predetermined properties, like a miniature instruction manual that quietly dictated what their spin would be before they left their shared origin point. Under this hidden variable theory, the wave function $p psi $ would not represent the full reality, but merely our limited knowledge of a reality that was, in fact, perfectly definite and pre-programmed all along. The particles were simply following their private, predetermined script. For nearly 30 years, the EPR paradox was simply a philosophical argument, a quiet debate over the nature of reality. Was the universe locally real and deterministic, Or was it non-local and probabilistic? The question remained an academic stalemate until the brilliant, quiet work of John Bell in the 1960s. Bell was able to take the philosophical assumptions of Einstein's local hidden variables and translate them into a concrete, mathematical prediction known as Bell's theorem. Bell showed that if Einstein's idea of local hidden variables were true, if reality was definite before measurement and effects could not travel faster than light, then the statistical correlation between the entangled particles, measurements would be limited by a certain maximum value. However, if the predictions of standard quantum mechanics were true, if the particles truly existed in a state of indefinite superposition until the wave function collapsed non-locally, then the correlation would be stronger than the local, hidden variable limit. Bell had turned a philosophical disagreement into a quiet, testable inequality. The subsequent experimental tests, carried out initially by scientists like John Clauser and later refined with incredible precision by Alain Aspect in the 1980s, stand as one of the most significant experimental feats in the history of science. These experiments involved separating entangled photons and measuring their polarization, an optical equivalent of spin, across distances of many meters, and later, many kilometers. The results were conclusive, defying the local realism that Einstein cherished. The correlation between the distant, measured photons consistently and repeatedly violated Bell's inequality by a wide margin. The correlations were exactly as strong as predicted by standard quantum mechanics. This finding carries a profound message. Reality is fundamentally non-local. It means that the universe operates in a unified, holistic way that defies our classical, separated intuitions. The entanglement bond is not a hidden communication system. It is a shared existence. The two particles are not two separate entities talking to each other. They are two manifestations of the same fundamental object, described by a single wave function that spans the entire distance. The distinction between them dissolves into a shared, indefinite potential. We must accept one of two quietly uncomfortable conclusions. Either reality is fundamentally non-local, where the measurement of one object instantly influences a distant, linked object, or it is fundamentally non-real, meaning that properties do not exist prior to measurement. Either way, the Newtonian intuition that the universe is made of discrete, independent, pre-existing things is wrong. The deeper structure of the cosmos is one of inherent interconnectedness, where the very act of observation here on Earth helps to define the state of matter 500 light-years away, a profound echo of the mythic idea of universal unity. The quiet revolution of entanglement forces us to confront the idea that separation might be an illusion of our macroscopic scale. But this shared, indefinite existence leads to the greatest question of all. If the fundamental building blocks of the universe are smeared out, entangled probabilities, why do we experience a world that is so completely, utterly definite? How does the definite, macroscopic reality we inhabit emerge from the fluid, probabilistic realm of the quantum? To resolve this, we must delve into the very nature of the measurement process itself and the strange, quiet role that information plays in bridging the two worlds. The great silence awaits us. The core difficulty of quantum mechanics, the one that troubles the philosophical sleep of physicists, is often called the measurement problem. The equations of quantum mechanics, specifically the Schrödinger equation, predict a universe of eternal, flowing superposition, where particles should remain in a ghostly, probabilistic blend of all possibilities forever. Yet, we live in a definite classical world. When we look at a cat, we see a cat that is either alive or dead, never a probabilistic mixture of the two, as famously outlined in Erwin Schrödinger's quiet thought experiment, designed to highlight the absurdity of applying quantum rules to the macroscopic scale. The question remains, what physical process takes the fluid, indefinite quantum wave function, $psi, and forces it into the sharp, definite reality of classical experience? For decades, the standard answer was vague, simply stating that the wave function collapses upon measurement or observation, a rule added by hand to the otherwise perfect mathematics. But this merely names the problem. It does not explain the mechanism. The key to bridging this chasm between the quantum and the classical lies in a concept called decoherence, a quiet, environmental mechanism that acts as the great translator between the realm of potentiality and the realm of actuality. Decoherence describes the process by which a quantum system loses its ability to exhibit wave-like behavior, such as superposition and interference, due to its unavoidable interaction with the surrounding environment. This interaction is not a focused measurement by a scientist, but simply the constant, chaotic contact with the thermal environment. Photons of background light, molecules of air, and the quiet, pervasive, gravitational, and electromagnetic fields that constantly buffet everything. Even in the deepest vacuum of space, the subtle energy of the zero-point field ensures no system is ever truly isolated. Imagine our single electron passing through the double slits in its state of superposition, taking both paths simultaneously. For this superposition to persist, the electron must remain perfectly isolated from the surrounding environment. If the electron, while in its ghostly superposition, quietly collides with a single photon from the background heat, or brushes against a single air molecule, information about its state is instantaneously recorded and scattered into the environment. This is the crucial step. The environment effectively measures the electron, not in the sense of a conscious scientist, but in the sense of a physical interaction that transfers information. This transferred information is then immediately spread, or decohered, across the almost infinite number of degrees of freedom in the surrounding environment. The environment becomes entangled with the electron state. If the electron was in a superposition of going through slit 1 and slit 2, the environment now exists in a superposition of electron went through slit 1 and electron went through slit 2. But because the environment is so vast, composed of trillions upon trillions of interacting particles, this environmental entanglement spreads the information so rapidly and thoroughly that it becomes practically irreversible and undetectable. It is like dropping a single drop of dye into a colossal ocean. The dye is still there, but it is so diffused that it is impossible to reconstitute the original droplet. The result is not that the wave function is physically destroyed, but that the electron's ability to interfere with itself, the signature of its quantum nature, is instantly destroyed. The probability amplitudes, the different possibilities in the superposition, lose their fixed relationship, and the quantum system quickly, quietly, settles into a probabilistic mixture of definite, classical possibilities. Decoherence effectively prunes the infinite branches of potentiality down to a limited set of choices, rapidly selecting the one, definite reality that we observe. The timescale of decoherence is the key to understanding why we do not experience a quantum world. For macroscopic objects, a baseball, a coffee cup, or a cat, The number of particles constantly interacting with the environment is astronomical. The rate of decoherence is blindingly fast, often occurring in femtoseconds, or $10, negative $15 seconds, a millionth of a billionth of a second. This process is so immediate and efficient that any macroscopic object is instantly and continuously decohered by its own existence, by the mere fact of being hot, massive, and surrounded by photons and air molecules. This is the quiet genius of the process. Our definite, classical reality is not a fundamental state. It is an emergent phenomenon, the inevitable, rapid outcome of massive quantum systems interacting with their environment. The larger and hotter an object is, the faster it decoheres, and the more classical it appears. This explains the quiet paradox of Schrödinger's cat. The cat, being a large, warm biological system, is constantly bombarded by background radiation and molecules, instantly decohering itself into a definite state, either alive or dead, long before the experimental observer opens the box. The superposition of alive and dead is merely a theoretical state that cannot persist for any measurable time in a system of that complexity and size. Decoherence is the bridge across the scale of reality, the physical mechanism that separates the elegant hesitation of the single electron from the definite certainty of your morning cup of coffee. This process also connects the concept of reality to the quiet flow of information. The transition from quantum to classical is the transition from a superposition of all possibilities to a simple, definite stream of classical information. The electron is at point $, x $, the cat is alive. Decoherence ensures that information about a system's state is copied and disseminated into the environment too quickly and massively for the system to ever return to its delicate, unified superposition. The classical world is defined by the easy accessibility of information, the fact that an object's position is a property available for all to observe, redundantly copied in the light scattered off its surface and the air molecules bouncing off its mass. Thus, the measurement problem is quietly transformed. The question is no longer, when does the wave function collapse? But how quickly does the environment force the system to lose its quantum coherence? The collapse is not a sudden, mysterious intervention of consciousness. It is the inevitable, continuous result of the relentless, background noise of the thermal environment. The quantum world is defined by its isolation and coherence. The classical world is defined by its constant, unavoidable conversation with the rest of the cosmos. This realization brings a new layer of quiet philosophical reflection. If our definite reality is merely the emergent result of continuous interaction and information loss, then the deeper structure of the universe is still fundamentally quantum, still fluid, and still uncertain. We only perceive certainty because we ourselves are vast, warm, highly decohered classical systems. We are creatures of the aftermath, living within the stable, high-probability pools, left behind by trillions upon trillions of rapid quantum collapses. This emergent definiteness, this stable illusion of certainty, is the final layer of the veil. To truly understand the full architecture of this reality, we must look not just at the particles that define mass, but at the very substance that defines the void itself, the quiet, persistent energy that fills the seemingly empty space. And that is where the deeper structure takes us, into the vacuum. Having established that our definite, classical reality is an emergent phenomenon, born from the rapid process of decoherence, we must now turn our attention to the environment itself. What is the true nature of the vacuum, the seemingly empty space that surrounds us and provides the background noise that causes quantum collapse? Under the classical intuition, a perfect vacuum is simply a void, the absence of matter and energy. But within the quiet, complex mathematics of quantum field theory, the void is anything but empty. It is a seething, humming plenum of potential, a constant, energetic sea known as the quantum vacuum, or the source of the zero-point energy. Quantum field theory, which unites quantum mechanics with special relativity, reframes the reality we have explored. Particles are not fundamental objects. They are instead localized excitations, or quiet vibrations, in underlying, ubiquitous fields that permeate all of space. The electron is an excitation in the electron field. The photon is an excitation in the electromagnetic field. In this view, even a volume of space that has been stripped of all matter and cooled to absolute zero, the coldest possible temperature, or 0 degrees Kelvin, still retains a minimal, inherent level of energy. This is the zero-point energy, the minimum necessary jitter of the quantum fields, a constant, baseline hum that can never be entirely eliminated. The uncertainty principle, which prevents a particle from having both a definite position and a definite momentum, dictates this perpetual motion of the vacuum. If the energy of a quantum field in a region of space were to drop perfectly to zero, that would imply a state of absolute certainty about its energy and its change in energy, which is strictly forbidden by the quantum rules. Therefore, the field must perpetually fluctuate, generating a constant, energetic oscillation even in the profound absence of matter. This fluctuation is not a philosophical idea, it is a mathematical necessity and the seventh great conceptual anomaly. These energy fluctuations in the vacuum manifest as the continuous, ephemeral creation and annihilation of virtual particles. Imagine a pair of particles, such as an electron and its antimatter twin, a positron, spontaneously blinking into existence from the raw energy of the vacuum, only to exist for a fleeting fraction of a second, governed by the time-energy form of the uncertainty principle, before quietly merging and vanishing back into the void. This process is happening everywhere, at all times, a constant, silent, energetic popping that fills every cubic centimeter of space. The vacuum is not a quiet abyss. It is a loud, energetic froth of potential. The reality of this zero-point energy is confirmed by two quiet, persistent experimental anomalies that serve as fingerprints of the humming vacuum. The first is the Lamb shift, a tiny, subtle shift in the energy levels of electrons in the hydrogen atom. According to the early, simple quantum models, certain energy levels should be exactly the same or degenerate, but precise measurements show they are slightly, persistently different. This discrepancy is perfectly explained by the electron constantly interacting with the swarm of virtual particles in the quantum vacuum, which subtly alters its potential energy and nudges the energy level away from the predicted value. It is as if the electron is constantly wading through a subtle, ephemeral fog. The second, and perhaps more visually compelling, piece of evidence is the Casimir effect. Imagine placing two perfectly parallel, uncharged metal plates very close together in a perfect vacuum, separated by a microscopic distance, say 400 nanometers, which is 400 billionths of a meter. These plates do not touch, and they have no external electric charge. yet they will quietly, persistently push toward each other. This is the eighth great conceptual anomaly. The classical world offers no explanation for this attraction, but quantum field theory does. The gap between the two plates restricts the wavelengths of the virtual photons that can spontaneously pop into existence between them. Only virtual photons, whose wavelengths fit neatly within the gap, are allowed. The space outside the plates, however, is unrestricted and can host virtual photons of all wavelengths. This means there is a lower density of virtual photons or lower energy density between the plates than there is outside. The pressure exerted by the external, greater density of virtual particles gently but persistently pushes the two plates together. The Casimir effect is, quite literally, a physical force generated by the absence of matter, a measurable manifestation of the energy of the quantum vacuum. The conceptual scale of this zero-point energy is staggering. When physicists use the full mathematics of quantum field theory to calculate the theoretical total energy density of this quantum vacuum, the result is immense, potentially leading to a number so vast that it exceeds the critical energy density needed to seal the universe shut into a black hole by 70 orders of magnitude. This monumental, theoretical discrepancy between the calculated zero-point energy and the observed small energy of the vacuum that drives cosmic expansion, known as the cosmological constant problem, is the single greatest outstanding puzzle in modern physics, a quiet, profound contradiction at the heart of our understanding of reality. This humming vacuum completely reframes our understanding of the void and, by extension, the process of decoherence. The environment that constantly monitors and collapses quantum superposition is not just the warm air or the visible light. It is the fundamental, energetic texture of space-time itself. The decoherence process, which forces the electron's fluid potential into a single point, is the electron's constant interaction with this fundamental, noisy energy of the void, a persistent, inescapable entanglement with the very fabric of existence. We find ourselves in a quiet, paradoxical position. The subtle structure of our definite, stable world emerges from the noise and energetic chaos of the quantum vacuum. The solidity of your chair is an emergent property created by the relentless, statistical certainty imposed upon its constituent atoms by a universal, energetic fog. The deepest structure of reality, then, is not a solid foundation, but a vibrating field of pure potential, a persistent hum that gives rise to all that is visible and yet remains perpetually unseen. To continue our quiet journey inward, we must now move from the substance of the void to the deeper, strange geometry of the space-time that contains it, and the concept that links the quantum realm to the force of gravity itself, searching for a single, unified theory. Our quiet journey has revealed a reality built upon superposition, probability, and a humming, energetic vacuum, a conceptual landscape utterly defined by quantum mechanics. Yet, lurking beneath this structure is a profound, unresolved dissonance, the ultimate barrier to fully understanding the secrets of quantum physics, the stubborn refusal of the force of gravity to participate in the quantum description. We possess two magnificent, exquisitely successful mathematical frameworks for describing the cosmos: quantum mechanics, which governs the incredibly small, the world of the particle, and the zero-point energy, and general relativity, Albert Einstein's beautiful geometric theory, which governs the incredibly large, the world of stars, galaxies, and the curvature of space-time itself. The deeper structure of reality cannot be complete until these two systems are reconciled into a single, quiet description. This is the problem of quantum gravity, the quiet search for unification. In quantum mechanics, all the fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, are understood to arise from the exchange of discrete, particulate quantum messengers, or gauge bosons. For instance, the electromagnetic force, which holds atoms together and governs the flow of light, is mediated by the exchange of photons. These forces are quantized. They are delivered in discrete packets, behaving according to the rules of probability and uncertainty. You can imagine the forces of the universe as being played out by tiny, continuous throws of quantum balls. General relativity, however, offers a completely different, geometric picture of gravity. It is not described as a force exchanged by a particle. Instead, gravity is the manifestation of the curvature of four-dimensional space-time caused by the presence of mass and energy. The Earth orbits the Sun, not because the Sun is pulling it with an invisible rope, but because the Sun's mass has gently warped the fabric of space-time around it, and the Earth is simply following the straightest possible path, a geodesic through that curved geometry. Space-time is not a static backdrop. It is a dynamic, elastic medium, and gravity is its quiet, elegant shape. The profound, conceptual conflict arises when physicists attempt to apply the rules of quantum mechanics to this smooth, continuous curvature of space-time. If gravity is a true force like the others, it must also be mediated by a quantum particle, a graviton, which would be exchanged between masses. But when theorists attempt to quantize gravity, the equations immediately break down. They yield infinite, nonsensical results that cannot be eliminated through the standard renormalization techniques that work for the other forces. The fundamental problem is that the quantum world is intrinsically defined by uncertainty and jitter, while Einstein's space-time is based on continuous, smooth, definite geometry. The difficulty becomes most acute at the smallest possible scale, a distance known as the Planck length, which is an unimaginably minute $10, -35. Dollar meters are zero, followed by 34 more zeros, and then a 1, measured in meters. At this scale, the quantum uncertainty in space-time itself becomes so enormous that the smooth fabric of space-time, predicted by general relativity, dissolves into a violent, turbulent foam, constantly bubbling and fluctuating. Trying to define a definite point or a smooth curve at the Planck scale is like trying to measure the perfect average height of a chaotic, crashing ocean wave during a hurricane. The two theories, quantum mechanics and general relativity, are mathematically and conceptually incompatible at this fundamental boundary, the quiet frontier of our knowledge. This conflict means that physics cannot describe what happens at the very beginning of the universe, the singularity of the Big Bang, or at the heart of a black hole, the gravitational singularity, which are the two most extreme environments. In the cosmos, where mass is compressed to an infinitely small volume, these are the 2 points where the scale of the quantum world meets the extreme curvature of the gravitational world, and where the current laws of physics fail completely. The physics we rely on simply has a massive, quiet conceptual hole at the most important moments of cosmic existence. In the pursuit of resolving this deep contradiction, two major theoretical frameworks have emerged: searching for a deeper structure that contains both quantum probability and gravitational geometry. The first is string theory, which quietly proposes that the fundamental constituents of the universe, the electrons, photons, and quarks, are not point-like particles at all, but incredibly tiny, vibrating one-dimensional strings, existing at the Planck length. The specific way a string vibrates dictates what kind of particle it is, whether an electron, a photon, or even a hypothetical graviton. The universe is rendered as a cosmic symphony of these vibrating strands. This framework naturally includes the graviton particle, unifying it with the other forces in a consistent, mathematically sound way. However, string theory requires the existence of many extra spatial dimensions, often 10 or 11 in total, which are unseen by us because they are curled up or compactified into a tiny, unobservable scale. It is a beautiful, quiet, mathematical edifice, but it remains, for now, a grand theoretical speculation, without direct experimental verification, waiting patiently for the technology capable of peering down to the Planck scale. The second major contender is loop quantum gravity, which takes a more conservative approach, focusing on quantizing space-time itself rather than introducing new objects like strings. It suggests that space-time is not smooth and continuous, but is instead woven from discrete, granular chunks of volume and area, like a piece of cosmic chainmail. The geometry of space-time, the curves that create gravity, arises from the quantum connections between these loops. This theory quietly suggests that at the Planck scale, space itself is quantized, with a minimum size below which nothing can exist. This framework avoids the infinite singularities and offers a picture of the Big Bang as a big bounce, where the universe collapsed from a prior existence before rebounding. The search for this unified theory, sometimes called the theory of everything, is driven by the quiet, philosophical conviction that reality must be fundamentally one, described by a single, coherent set of rules. The dissonance between the quantum jitter and the gravitational curve is the final great intellectual challenge. If we can understand the nature of space-time at the Planck scale, we will have reached the deepest structure available to us, resolving the contradictions that have haunted physics for a century. The final secret of quantum physics is the secret of space-time itself, the quiet fabric upon which the drama of probability unfolds. And to continue our quiet journey, we must now move from the fundamental strings and loops to the implications of this deep structure on the nature of information, which is the final, strange conceptual currency of the quantum world. Our quiet exploration has moved from the particle's hesitation to the energetic hum of the vacuum and the deep geometrical conflict with gravity. To bridge these enormous conceptual distances, modern physics increasingly turns to an even more abstract, yet fundamentally critical concept: information. In the deepest structure of reality, information is not merely a description of the universe. It might be the very substance of the universe, the quiet currency exchanged during every interaction, collapse, and decoherence. The shift in perspective suggests that the laws of physics are fundamentally laws about the storage, transfer, and loss of information. Under the classical, deterministic view, information was simple. The total information of a system was the collection of every particle's position and momentum, and the laws of physics were merely the rules that predicted how this information changed over time. But in the quantum realm, the picture becomes complex. As we learned from the measurement problem, a quantum system in superposition contains a vast amount of potential information, a blend of all possibilities described by the wave function. The act of measurement, the wave function collapse, is essentially an act of information transfer, reducing the continuous, infinite potential information of psi into a single, definite, classical piece of information. The electron is here. This link between physics and information is most powerfully illuminated through the concept of entropy. In thermodynamics, entropy is usually described as a measure of disorder, the quiet, relentless arrow of time that pushes systems toward a state of uniform randomness. If you leave a cup of hot coffee in a room, the heat will inevitably spread until the entire room, and the coffee reaches the same temperature, a state of maximum entropy or maximum disorder. In the information context, entropy is a precise measure of the missing information required to fully specify the state of a system. A definite, perfectly organized system has low entropy. A chaotic, random system has high entropy because a great deal of information is needed to describe its exact microscopic state. The core principle governing all known physical processes is the second law of thermodynamics, which quietly dictates that the total entropy of the universe can never decrease. It can only increase or remain constant. This is the ultimate law of information, loss, and dispersion. Every physical process, from the burning of a star to the simple act of observation, generates an irreversible amount of entropy, a constant, quiet tax on order. When a quantum wave function collapses, the process of decoherence and measurement generates entropy. The original, coherent information contained in the superposition is lost to the environment, diffused across countless degrees of freedom, an event that is physically irreversible. This idea leads to a profound connection between the micro world of quantum physics and the macro world of cosmology, the ninth great conceptual anomaly. The connection appears most dramatically in the study of black holes, the cosmic regions where gravity is so intense that nothing, not even light, can escape. Classically, a black hole was defined purely by three properties: its mass, its angular momentum, and its electric charge. Everything that fell into it, a book, a planet, or a stream of pure information, was lost forever. This posed a serious problem for information conservation, a principle fundamental to quantum mechanics. If information about the objects falling into the black hole was genuinely destroyed, it would violate the principle of unitarity, which states that the total quantum information of the universe must be conserved. The solution came from the brilliant, quiet work of Jacob Bekenstein and Stephen Hawking. Bekenstein proposed that a black hole must possess entropy, a measure of its internal disorder, and the missing information about the matter that formed it. He found that the black hole's entropy was not proportional to its volume, as one might expect for a three-dimensional object, but was proportional to the area of its event horizon, the two-dimensional boundary from which nothing can return. This was a radical suggestion, implying that the total information content of a three-dimensional volume might be encoded entirely on a two-dimensional surface. Hawking further revolutionized this concept by demonstrating, through subtle quantum calculations, that black holes are not perfectly black. Due to the creation of virtual particle pairs near the event horizon, a manifestation of the zero-point energy, a black hole must slowly and quietly radiate energy, a process now known as Hawking radiation. Because this radiation carries energy, the black hole slowly shrinks and will eventually over an unimaginable period of time, entirely evaporate. This result strongly supported the thermodynamic nature of black holes, but it deepened the information paradox. If the black hole evaporates completely, and the Hawking radiation it emits is purely thermal, meaning it contains no information about the specific objects that fell in, then where does the information go? Does it truly disappear, or is it merely scrambled and encoded into the subtle quantum correlations of the radiation itself? The most striking implication of this thermodynamic analysis of black holes is the holographic principle. This principle, initially proposed to resolve the information paradox, suggests that the entire three-dimensional universe we perceive might be a kind of hologram. That is, all the information needed to fully describe our vast, three-dimensional reality might be entirely encoded on a distant, two-dimensional boundary, like the surface of a bubble surrounding the cosmos. Just as a two-dimensional film contains all the information necessary to project a three-dimensional image, our universe may operate on the same quiet, underlying geometric trick. This deep structure is one where information is the primary reality. The physical objects, the particles, the geometry of space-time might all be emergent phenomena, complex projections arising from a fundamental, informational substrate. The universe becomes the ultimate cosmic ledger, and the laws of physics are the rules that govern how information is accounted for. The quiet flow of time, the collapse of the wave function, and the very existence of entropy are all tied to the fundamental processes of information being generated, conserved, and inevitably dispersed into the environment. This means that the fundamental act of being a classical observer, the process of measurement and decoherence, is an information-generating, entropy-increasing process. When we look at the quantum world, we are trading the elegant, subtle information of superposition for the coarse, definite information of a single, classical state. And this trade costs the universe a small, constant amount of thermodynamic order. To truly complete our reflection, we must now turn our attention away from the abstract currency of information and look at the final frontier, the implications of all these quiet quantum secrets for the nature of consciousness itself. Our quiet journey through the deepest structure of reality has brought us to the threshold of the most difficult, most profound question: the link between the objective, probabilistic realm of the quantum and the subjective, definite experience of consciousness. We have established that the definite, classical world emerges from the fluid quantum potential through the process of decoherence, an unstoppable physical process driven by environmental interaction and the relentless flow of information. But if decoherence is a purely physical, non-conscious mechanism, why is the term observer still so often used in the discussion of wave function collapse? What, precisely, is the role of the thinking, feeling human consciousness in this final act of defining reality? This connection, or lack thereof, is the ultimate point of friction between physics and philosophy, the 10th great conceptual anomaly. The conceptual tension is best understood by returning to the measurement problem. If the entire universe, including the observing apparatus and the scientist, is made of quantum particles, then the entire system should, mathematically, be governed by one colossal wave function. The Schrödinger equation, being perfectly linear and deterministic, predicts that the act of measurement does not cause a collapse. It merely extends the superposition. If the electron is in a superposition of spin up and spin down, and the detector is in a superposition of measured spin up and measured spin down, then the final state of the entire system, including the scientist's brain, should, theoretically, be a superposition of two macroscopic realities, one where the scientist sees spin up and one where the scientist sees spin down. This is where consciousness often re-enters the conversation. If all the physical parts of the system, the particle, the detector, the air, the room, and the neurons in the brain can all be described by a linear quantum equation that never predicts collapse, then the collapse itself must occur outside that physical description. Some interpretations of quantum mechanics, such as the von Neumann-Wigner interpretation, quietly suggest that the final collapse of the wave function, the transition from the superposition of possibilities to the single, definite experience only happens when the information reaches a conscious mind. In this view, consciousness itself, by being non-physical, or at least operating under rules yet unknown, is the ultimate non-linear agent that forces the final, irreversible transition. The universe, in this quiet, profound sense, waits for a mind to finalize its reality. However, the majority consensus in physics leans away from placing consciousness in this causal role, favoring the robust physical explanation of decoherence. The decoherence approach argues that the scientist's brain, being a vast, warm, highly complex system of trillions of neurons firing in a humid, electromagnetic environment, is the most decoherent system in the universe. The transition from the quantum world to the classical world is so fast and so complete at the level of the brain that the subjective experience of certainty, I see spin up, is simply the consequence of the brain, as a physical object, being rapidly and continuously decohered. The mind is not the collapse agent. It is the ultimate recipient of the already collapsed, definite information. The term observer merely stands in for the point at which the irreversible process of information copying and environmental entanglement becomes complete. But the quiet philosophical question remains: even if the environment causes decoherence, what exactly experiences the single outcome? Why does the subjective reality of the scientist not contain the superposition? This enduring mystery has led to the development of radical, conceptually demanding interpretations, such as the many worlds interpretation proposed by Hugh Everett in the 1950s. This interpretation accepts the full, quiet logic of the Schrödinger equation, taking the linearity to its absolute conclusion. It states that the wave function never collapses. Instead, every time a quantum measurement or interaction occurs, the entire universe, including the observer, instantly splits into a multitude of parallel universes, each one corresponding to one of the possible outcomes. In the case of the electron, one version of you instantly exists in a universe where you saw spin up, and another version of you instantly exists in a separate, equally real universe where you saw spin down. The vast, universal wave function, containing all possibilities, simply evolves continuously, and the splitting process, though perhaps initiated by decoherence, is the mechanism by which we perceive our particular, definite reality. The quiet humor is that you are, right now, in a superposition of billions of identical yous across a nearly infinite number of parallel realities, but your consciousness, your subjective experience, only perceives the history of one branch, one single definite outcome. This constant, quiet splitting of the universe suggests a deep structure where all potential realities are equally real and our perceived certainty is merely an artifact of our own subjective trajectory through the branching cosmos. The implications for consciousness are profound. It is not a mysterious force that collapses the wave. It is an index that selects one branch of the constantly growing cosmic tree. The single, definite reality you experience is merely the branch you happen to be on. Ultimately, the deepest secret of quantum physics may be that the nature of consciousness itself is what defines the boundary of the classical world. If consciousness is merely an emergent property of complex physical systems, then the definite reality we experience is simply the consequence of our massive, warm brains being relentlessly decohered. But if consciousness has a non-physical aspect, the quantum boundary may extend into the very mechanism of perception, allowing the mind to subtly influence the flow of reality at the highest level of information processing. The debate continues in the quiet chambers of theoretical physics. Does the definite world emerge from physical interaction alone, or does the final moment of collapse require the subjective experience of a mind? The answer dictates whether the universe is purely an objective, self-contained machine or a participatory, fundamentally subjective experience. This question brings us to the end of the inquiry into the hidden structure of reality, prompting us to pause and reflect on the quiet, human response to the uncertainty we have discovered. We have explored the elegance of possibility, the persistence of probability, and the power of the infinitesimal. We must now turn our attention to the human reflection that seeks meaning within this cosmic hesitation. The elegance of the Schrödinger equation, which so beautifully describes the smooth, continuous evolution of a probability cloud, contained within it a quiet, unsettling monster, the problem of collapse. If the wave function governs all quantum entities, and everything is ultimately made of quantum entities, then where, exactly, does the quantum world end and the classical world of certainty begin? This question, this profound gap between possibility and fact, drove the equation's own creator, the gentle physicist Erwin Schrödinger, to devise a conceptual nightmare designed to demonstrate the inherent absurdity of applying the rules of the microcosmos to the world of cats and clocks. Imagine now, in the stillness of this late hour, the construction of this infamous thought experiment. You place a living, breathing cat inside a perfectly sealed, opaque steel chamber. Alongside the cat, you install a delicate apparatus, a single radioactive atom that, within a period of 60 minutes, has precisely a 50% probability of decaying and a 50% probability of remaining stable. This is our quiet quantum coin flip, the engine of uncertainty. Attached to this atom is a Geiger counter, set up to detect the decay event. If the atom decays, the counter triggers a small hammer, which immediately smashes a tiny vial of prussic acid, a lethal poison. If the atom does not decay, the hammer remains still, and the cat remains perfectly healthy. The atom, according to the principles of the wave function that we explored, exists in a state of superposition until it is measured. It is simultaneously decayed and not decayed. Its probability cloud, the smear of potential, holds both realities in equal measure. But here is where the absurdity quietly settles in, forcing a contradiction upon your logical mind. The fate of the entire macroscopic apparatus, the hammer, the vial, the poison, and, critically, the cat, is directly, mechanically linked to the quantum state of that single, subatomic particle. The rules of quantum mechanics dictate that as long as the box remains sealed, the entire system must be described by a single, encompassing wave function that smoothly evolves over time, following the logic of the elegant equation. Therefore, until an external observer opens the steel chamber and performs the final measurement, the cat itself must be described by a superposition state. In this strange, mathematical sense, the cat is simultaneously an extremely unhappy, dead cat and a perfectly healthy, living cat, a duality that is utterly meaningless in the world of our lived experience. The concept of an entity being both alive and deceased at the same time is the ultimate defiance of the principle of non-contradiction, the fundamental cornerstone of classical reality. Schrödinger intended this thought experiment to be a subtle piece of scientific humor, a reductio ad absurdum that exposed the incomplete nature of the theory. The particle refuses to make eye contact not just with the detector, but with the poor feline locked in the box. The paradox compels us to ask, at what point did the reality solidify? Did the wave function collapse when the atom decayed? Or when the Geiger counter registered the decay? Or when the hammer moved? Or only when the scientist, having waited precisely 1 hour, opened the box to look inside? If you choose the latter, you are granting a profoundly powerful, almost cosmic role to the act of observation, suggesting that the consciousness of the physicist is what performs the final cut, splitting the probability pool into a single, undeniable fact. If you choose an earlier moment, say, the moment the Geiger counter registered the click, then you must acknowledge a moment when the quantum uncertainty was transferred to the macroscopic world, only to disappear instantly. The measurement problem is thus revealed as the problem of defining the boundary between the smooth determinism of the equation and the sudden, random commitment to fact. This paradox forces a quiet revolution in our thinking about reality. It implies that the world we perceive, the world of definite outcomes, must be continuously created, moment by moment, through endless, instantaneous collapses. The only difference between the electron in the double-slit experiment and the cat in the box is the sheer scale of the possibilities. For the cat, the possibilities are only 2 dead or alive, while the electron possesses an infinite gradient of potential locations. Yet, the governing principle remains the same. Reality is potential until it is witnessed. The scientific community has, over time, developed theories that attempt to solve this uncomfortable absurdity, most notably through the concept of decoherence, a process we will explore later in our quiet journey. Decoherence suggests that the superposition of a large, complex system like a cat is instantly and irrevocably destroyed by its interaction with the incredibly vast number of particles in its environment, the air, the heat, the photons inside the box. These environmental interactions perform countless silent measurements every picosecond, effectively collapsing the wave function so rapidly that the cat never truly gets to experience its bizarre duality. For all intents and purposes, the cat is quickly forced to choose a singular fate by the sheer noise of its environment, thereby maintaining the illusion of a classical, certain world. But even if decoherence explains why we never see a blurry, half-dead, half-alive cat, it does not erase the foundational truth revealed by the box. The underlying reality is governed by potential. The universe is composed of possibilities, and only through the relentless interactions and commitments of measurement do we experience the rigid, seemingly factual world of our daily lives. This thought experiment stands as a silent monument to the power of quantum weirdness, a humorous yet profound challenge to the very definition of being. To understand this challenge fully, we must now turn our attention from the spatial paradox, the particle existing in two places, to the temporal paradox, the idea that quantum events can be linked across vast distances with zero time lag. This non-local connection, this strange, instantaneous tether between particles that have once interacted, takes us even further away from the comfortable logic of the classical world. We must investigate the relationship that Albert Einstein famously and humorously called spooky action at a distance. Our quiet journey has revealed that the quantum world is fundamentally probabilistic, with particles existing as possibility pools until the moment of commitment. This inherent uncertainty led the brilliant and quietly irreverent physicist Richard Feynman to develop a radical, profound, and visually stunning formulation of quantum mechanics known as the sum over histories, or the path integral formulation. This concept suggests a truth more bizarre than anything we have explored. A particle, in moving from point A to point B, does not follow a single, definite path, but simultaneously explores every conceivable path in the universe. Imagine watching a single electron travel across a small space. Classical physics, the world of shadows on the cave wall, dictates one simple, elegant path, the trajectory that minimizes action, much like the path a cannonball takes when it flies through the air. But according to Feynman's grand idea, the electron explores every possible route imaginable. It travels in a straight line. It spirals wildly. It flies off into the Andromeda Galaxy before quietly returning to hit the target, and it even moves backward in time, all at once. The genius of the path integral formulation is that it is a direct mathematical embodiment of the principle of superposition and the wave nature of matter. It states that the probability amplitude, the quantum equivalent of probability, for the particle to go from A to B, is found by adding up, or summing, the contributions from every single possible path the particle could take between those 2 points. Each path has an associated probability amplitude, which is a mathematical representation of a wave. Here is where the quiet tension of the mathematics resolves into the certainty of our perceived world. For most of these wildly improbable paths, the spirals, the zigzags, and the journeys backward in time, the corresponding wave amplitudes are so varied and numerous that they interfere with each other destructively. A path traveling slightly off the classical route will have its wave amplitude perfectly cancelled out by a path traveling slightly off in the opposite direction. They are the quiet, statistical noise of the cosmos, cancelling each other out to create a stable silence. However, there is one set of paths, a narrow corridor of trajectories that are very close to the classical path, the one dictated by the familiar laws of least action. For these paths, the wave amplitudes are nearly identical, and they constructively interfere, reinforcing each other powerfully. When you sum over all of the histories, the contribution from the classical, expected path overwhelmingly dominates the final probability. The humor in this lies in the fact that the classical world is not a fundamentally different reality from the quantum world. It is merely the place where all the wildly improbable quantum possibilities cancel each other out through destructive interference, leaving only the single, highly probable path that we perceive. Our world of certainty, of fixed facts and predictable motion, is the result of a massive, subtle, quantum self-cancellation. The universe only appears deterministic because the wave amplitudes for the improbable paths ultimately refuse to make eye contact with reality. The philosophical implication of the sum over histories is stunning. It suggests that probability is not merely a description of our ignorance, but a core, active element of reality. The particle, in its quiet hesitation, truly exists as a superposition of all these potential histories simultaneously, with the classical path being the single history that survives the ultimate quantum veto. This explains, with elegant simplicity, the bizarre behavior of the double-slit experiment. When the two slits are open, the particle's probability amplitude is the sum of all paths passing through the left slit, plus the sum of all paths passing through the right slit. The resulting interference pattern is simply the constructive and destructive interference of these two sets of histories, proving the particle truly explored both possibilities. The path integral formulation provides a powerful, unifying language for quantum field theory, allowing physicists to quietly calculate interaction probabilities and to describe the behavior of virtual particles. The creation and annihilation of virtual particles, which we explored in segment 8, are, in this view, just tiny, closed loops of histories where a particle travels a path forward in time and its antiparticle travels the same path backward in time, ultimately contributing to the zero-point energy of the vacuum. As we reflect on Feynman's grand idea, we realize that the universe is not just a place where quantum events are random. It is a place where every possibility is genuinely explored, where the fabric of reality contains the record of all potential actions. This concept that every potential path contributes to the final outcome is the ultimate philosophical link to the human experience of choice and consequence. Our reality is the path that survived the quantum cancellation. This movement through all of time and space leads us naturally to the next great mystery, a phenomenon that challenges our very definition of what a particle is. We must now turn to the subtle art of identity and ask, if all electrons are identical, how can we tell them apart? The answer leads us to a fundamental symmetry and a new kind of cosmic bookkeeping. Our quiet exploration of the deeper structure brings us to a final, profound echo from the wellspring of Western philosophy, an image devised over 2 millennia ago that serves as a chillingly accurate metaphor for the difference between the classical, perceived world and the true, quantum reality, Plato's allegory of the cave. This allegory, contained within Plato's great dialogue, The Republic, asks us to contemplate whether our sensory experience is merely a pale, derived version of a richer, more fundamental truth. Imagine yourself now among the quiet prisoners, chained, since birth, in a deep, dark cavern. Their necks and legs are fixed, forcing them to look only forward, at the back wall of the cave. Behind them, unseen, a fire burns, and between the fire and the prisoners, others walk, holding up various artificial objects, statues, and figures. The only thing the prisoners can ever see, hear, or know are the two-dimensional shadows cast by these objects onto the wall before them. They would name the shadows, categorize them, and believe, with absolute certainty, that these flat, flickering forms constitute the entirety of true reality. Their science, their common sense, their shared life experience, all are based on the deterministic, singular nature of the shadows. This world of shadows is the classical, Newtonian world of our macroscopic experience. It is the world where objects have definite properties, where causes strictly follow effects, where time moves forward predictably, and where all reality seems to be composed of fixed, distinct facts. The shadow of a statue, for instance, has a definite size and location. It is either here or there, and it follows a clear, linear trajectory across the wall. The prisoner's intuition, like that of the classical physicists, is one of certainty, locality, and fixed outcomes. Now, contemplate the true objects and the firelight behind them. These unseen, three-dimensional entities, the statues and figures that cast the shadows, represent the underlying, fundamental reality, the quantum world. The quantum world is inherently richer, more complex, and vastly different from its projected shadow. An electron, before observation, is not the point-like shadow the detector registers. It is the complex, shimmering, multi-dimensional reality of the wave function, simultaneously occupying many potentials, a cloud of possibility that exists in a strange, abstract space we call Hilbert space. When a quantum measurement is performed, the moment we look at the electron, it is analogous to the light from the fire hitting the three-dimensional object and projecting a single, flat shadow onto the wall. The act of observation is the act of projection, reducing the rich, probabilistic, high-dimensional reality of the wave function, the true object, into the singular, definite, low-dimensional reality of the classical fact. The shadow, the collapse of the wave function, is simply the process of flattening the true object into a mere silhouette. The quiet, subtle humor of the situation lies in the quantum particle's inherent refusal to be a single, flat shadow until forced. As long as the electron remains unmeasured, it maintains its full, three-dimensional, wave-like existence. The moment we try to find its definite position, we force it to cast a shadow on the wall of our perception. And what is the Heisenberg uncertainty principle but the unavoidable blurring that results from trying to define a three-dimensional object too sharply by its two-dimensional projection? You cannot know the true object's full depth and its exact motion simultaneously merely by looking at its shadow. Plato's allegory also provides a profound, subtle understanding of entanglement. If two statues, two true objects, are linked together such that if one moves, the other must instantly move in the opposite direction, their shadows on the wall would also be perfectly, instantaneously correlated. To the prisoners, this would seem like spooky action at a distance between two shadows, as if one shadow magically influences the other without communication. But the person who has left the cave, the liberated philosopher, knows the truth. The correlation is not due to a communication between the shadows, but to the single, shared, unseen reality of the true, linked objects behind them. Entanglement, in this quiet, philosophical sense, is merely the perception of a single, indivisible quantum reality from our position as chained observers of shadows. This ancient framework offers a path to a quiet acceptance of quantum mystery. The strangeness of the quantum world is only strange when viewed from the perspective of the shadow world of fixed facts. If we accept that the wave function, the probabilistic field, is the fundamental reality, the forms, in Plato's original language, the true objects of the cosmos, then the classical world, the world of certainty and definite outcomes, is merely the inevitable, simplified image cast by that deeper structure onto the wall of our sensory experience. We are all quiet prisoners, shackled by the unavoidable interaction of decoherence, forced to perceive the universe as a series of simple, distinct shadows. But through the subtle mathematics and the precise experiments of the modern physicist, we gain a brief, profound glimpse of the true, flowing, multidimensional light source behind us. The purpose of this entire quiet documentary is to unchain your mind just enough to sense the full reality of the true objects, to hear the soft whispers of the probability fields just beyond the 2 dimensions of the shadow wall. This quiet, contemplative understanding of reality's hidden depths now provides the conceptual lens through which we can explore more of the deeper structure. We will now turn our attention from philosophical models back to the most bizarre, active behaviors of the quantum particle, the phenomena that truly defy the classical logic of the shadows, beginning with the astonishing act of passing through a wall. Our ongoing reflection on the probabilistic nature of reality leads us to a phenomenon that embodies the purity of quantum chance: radioactive decay. This is the quiet, ceaseless process by which unstable atomic nuclei spontaneously transform, emitting particles and energy, and it is a process that is utterly beyond any possibility of classical prediction. Image illustrating radioactive decay, showing a nucleus emitting an alpha particle. Imagine a single, unstable nucleus, such as an atom of carbon-14 or uranium-238. The internal workings of this nucleus, the complex forces and quantum tunneling possibilities that lead to its decay, are governed by the same wave function dynamics we have been exploring. Within a collection of these atoms, we can state with absolute precision the half-life, the specific amount of time required for exactly half of the original atoms to decay. For example, the half-life of carbon-14 is approximately 5,730 years, a time marker written in full words that allows us to date ancient artifacts with quiet confidence. However, here is the critical distinction, the quiet tension that defines this phenomenon. While we can predict the average, collective behavior of billions of atoms with great accuracy, we cannot, under any circumstances, predict the exact moment of decay for a single atom. No amount of classical knowledge, no measurement of its position, its momentum, or its temperature will ever allow us to know when that individual nucleus will decide to transform. The particle refuses to yield its secret. The decay of a single atom is the perfect, pure quantum coin flip, an event governed by irreducible randomness. The quantum wave function of the nucleus evolves smoothly, dictating the probability that the nucleus will decay over time. But the moment the decay actually occurs, the wave function collapses instantaneously, and the nucleus commits to its final, singular state. This commitment is entirely random, a demonstration that chance is a fundamental, non-negotiable feature of the universe's design, not a flaw in our understanding. This pure randomness is fundamentally different from classical unpredictability. If you flip a classical, physical coin, the outcome appears random, but it is, in principle, perfectly deterministic. If you knew the initial force of the flip, the air currents, and the moment it was caught, you could, with enough computational power, predict the result with certainty. The apparent randomness is simply due to a lack of precise information, a deficiency we call epistemic uncertainty. But the radioactive decay of a single atom is dictated by ontological uncertainty, meaning the randomness is inherent in the very nature of reality. The wave function, the most complete description of the system possible, only provides the probabilities. It contains no hidden information, no secret instruction, no Democritean hidden variable that preordains the moment of decay. The universe, at this fundamental level, genuinely chooses from the available potentials at the last possible moment. The process of decay is itself an exquisite example of quantum tunneling. The particles that escape the nucleus, such as alpha particles, 2 protons and 2 neutrons, are trapped within a fierce potential energy barrier created by the strong nuclear force. They do not have enough energy to jump over this barrier. Instead, they constantly tunnel back and forth within the confines of the nucleus until, at a completely random moment dictated by probability, they manage to tunnel through the barrier and escape. The half-life, in essence, is the average time it takes for half the wave functions to finally leak out. The philosophical implication of this perfect coin flip is immense. It underpins the reality we experience, providing the constant, low-level heat that drives geological processes within the Earth, and quietly governing the dating of every ancient object found by archaeologists. But its most profound statement is about freedom and determinism. If the universe at its foundation is fundamentally random, then the possibility of genuine novelty and non-deterministic events is woven into the very fabric of existence. The certainty of our macroscopic world is a statistical illusion, the quiet, stable surface generated by the averaging of countless, tiny, random decisions made at the quantum level. The deeper structure of reality is thus one where deterministic evolution, the smooth flow of the half-life curve for a large collection, coexists with irreducible randomness, the fate of a single atom. This tension between the absolute certainty of statistical averages and the absolute randomness of individual events is one of the most elegant, quiet paradoxes of the quantum world. As we move forward, we take this quiet acceptance of inherent chance and apply it to a larger, more abstract concept. We have seen how particles tunnel through space. Now, we must investigate how probability allows them to tunnel through time itself. We transition from the single, random commitment of decay to the grand, philosophical implications of a principle that suggests a particle explores every path, every possibility, simultaneously, in what is perhaps the most audacious conceptual leap of the modern era. We have explored the wave nature of matter, the absurdity of the cat's superposition, and the instantaneous, shared destiny of entangled particles. All these anomalies point to a universe that is fundamentally probabilistic, where certainty is only a fragile, fleeting condition. Now, we arrive at the most foundational restriction on our knowledge of this probabilistic world, a principle so deep it is woven into the very mathematics of the wave function, the Heisenberg uncertainty principle. The principle, formulated by the quiet, contemplative Werner Heisenberg, states that there is a fundamental, inescapable limit to the precision with which certain pairs of physical properties of a particle, such as its position and its momentum, can be known simultaneously. Momentum, as you know, is the simple, quiet combination of mass times velocity, the measure of an object's tendency to keep moving. Position is, simply, where it is. The uncertainty principle is not a statement about the clumsiness of our tools or the limits of our engineering. It is a profound, inherent property of reality itself. Imagine watching a single electron as it flies through space. If you attempt to pinpoint its precise location, to know its position with absolute certainty, the fundamental nature of the universe dictates that you must sacrifice all knowledge of its momentum. The act of precisely locating it fundamentally blurs its motion. Conversely, if you measure its momentum with extreme accuracy, its precise position instantly smears out, becoming a widely distributed probability pool across a vast area. The product of the two uncertainties, the uncertainty in position multiplied by the uncertainty in momentum, can never drop below a tiny, fixed value, a constant of nature related to Planck's constant, a measure of the graininess of energy. To understand this quiet, inescapable trade-off, you can reflect back on the wave nature of the electron. When an electron is acting like a wave, its position is, by definition, spread out, like a ripple on a pond. It does not have a single, definite location. When its position is spread out, its wave packet is long and smooth, and the mathematical analysis of that smooth wave allows you to calculate its momentum with great precision. Conversely, if you want to localize the electron, to make its position very precise, you must compress its wave function into a tiny, sharp spike. To create such a sharp, localized spike, you must mathematically combine many waves of different wavelengths. And since wavelength determines momentum, combining many different wavelengths introduces a large, unavoidable spread, or uncertainty, in the momentum. The trade-off is thus baked into the very definition of a wave. An electron cannot be both a perfectly sharp point, precise position, and a perfectly smooth, single frequency ripple, precise momentum, simultaneously. Reality, it seems, has decided that to be something, it must be fuzzy in some complementary way. This is the quiet, foundational limitation, a cosmic check and balance that prevents us from ever achieving complete knowledge of the micro-world. This principle is another of the great experimental anomalies that confirm the inherent strangeness of the universe. It shattered the comfortable dream of determinism, the idea held since the time of Pierre-Simon Laplace, that if we knew the exact position and momentum of every particle in the universe at any one moment, we could predict the entire future with absolute certainty. Quantum mechanics, through Heisenberg's principle, quietly closed the door on that dream. The universe is not a perfectly predictable clockwork mechanism. It is a mechanism where certain essential pieces of information are fundamentally unknowable at the same time. The particle simply refuses to surrender both pieces of information simultaneously. The philosophical implications of the uncertainty principle are immense. It introduces true, irreducible randomness into the foundation of reality. The outcome of a quantum coin flipped the decay of a radioactive atom. The path an electron chooses is not merely due to our lack of information. It is intrinsically random. The universe, in its quiet wisdom, incorporates chance as a primary feature, not a bug. This quiet acceptance of chance is what separates the quantum world from the classical. For systems of our scale, the human body, a falling apple, or a moving train, the constant in the equation, Planck's constant, is so incredibly small that the resulting uncertainty is completely negligible, far smaller than our most sensitive instruments can detect. This is why we experience a world of certainty and definite trajectories. But at the subatomic level, this uncertainty dictates everything, creating the probability clouds, the superpositions, and the strange interconnectedness we have been exploring. As we conclude this segment on the deep, quiet evidence, we have established three key anomalies: the wave-particle duality, the non-locality of entanglement, and the irreducible uncertainty in measurement. These three pillars, the double-slit pattern, the violation of Bell's inequalities, and the experimental confirmation of the Heisenberg limit, form the foundation of our modern, strange understanding of the cosmos. We now transition from the evidence gathered in the modern laboratory to the quiet, subtle echoes of these ideas found in the distant past. It is time to see how the ancients, through philosophy and myth, wrestled with the same dualities, the same unseen structures that now challenge the experimental scientist. We move from the cool light of the physics lab to the contemplation of antiquity, beginning our next emotional rhythm. Following the grand notion that a particle explores all possible histories, we encounter a fundamental, quiet truth about the quantum constituents of the universe. They possess an absolute and total lack of individuality. This truth is known as indistinguishability, and it introduces a new kind of cosmic mathematics that separates the quantum world from the classical world with profound, subtle finality. Imagine a handful of classical objects, say, marbles. Even if the marbles appear perfectly identical to your eye, they are fundamentally distinguishable. You could quietly mark one with a tiny scratch, or track its path from the moment it leaves your hand. In principle, you can always know which marble is which, a knowledge that underpins the entire mathematics of classical statistics. Now, consider a collection of 2 electrons, or 2 photons. In the quantum realm, these particles are absolutely, perfectly identical in every single intrinsic property: mass, charge, spin. But the profound difference lies in the fact that they are also indistinguishable. You cannot, even in principle, mark one or track its path. If you swap electron 1 with electron 2, the physical state of the entire system remains completely unchanged. This quiet lack of identity is not a practical limitation. It is a fundamental law of physics. The electron refuses to have an identity beyond the field that creates it. This inherent indistinguishability forces the mathematics of quantum mechanics to adopt a fundamentally different type of statistics, one that leads directly to the periodic table of elements, the stability of matter, and the very nature of light. When dealing with a collection of indistinguishable particles, the probability of finding the system in a certain state must be calculated differently than for classical, distinguishable marbles. This subtle shift in cosmic bookkeeping splits all fundamental particles into 2 great archetypal families, based on how their collective wave function behaves when 2 identical particles are swapped. First, there are the fermions, named after the great physicist Enrico Fermi. These particles include the electron, the proton, and the neutron, the constituents of matter. Fermions obey what is known as the Pauli exclusion principle, an extra layer of quiet, non-negotiable certainty imposed by the universe. This principle states that no 2 identical fermions can occupy the exact same quantum state, the same position, momentum, spin, and energy level at the same time. This is the great cosmic law of individuality that governs matter. Imagine building an atom. The Pauli principle forces electrons to stack up in distinct, sequential energy shells, like levels in a parking garage. It is this fundamental exclusion principle, arising from indistinguishability, that ensures the chemical diversity of the universe. If all electrons could occupy the lowest energy level, all atoms would collapse into a single, monotonous soup. Instead, the universe insists on diversity, quietly constructing the periodic table, which is built upon the forced segregation of indistinguishable electrons. Second, there are the bosons, named after the physicist Satyendra Nath Bose. These particles include the photon, the carrier of light, and the Higgs boson. Bosons are the opposite of fermions. They are communal and gregarious. They feel no obligation to the exclusion principle and actively prefer to occupy the exact same quantum state. They are happy to pile into the same energy level, all vibrating with the same frequency. This tendency of bosons to clump together in the same state is what drives phenomena like the intense, coherent light of a laser and the remarkable friction-free flow of superfluid helium, where countless atoms behave as a single, macroscopic quantum wave. The philosophical reflection here is profound. The universe is built from two opposing, complementary archetypes: the individualistic, exclusionary, matter particles, fermions, and the communal, clumping force-carrying particles, bosons. The very structure of reality, the tension between matter and energy, is dictated by a fundamental rule of identity regarding whether a particle refuses to share a quantum state or prefers to share it. This quiet distinction, emerging from the simple notion of indistinguishability, dictates why a solid object is solid, fermions refuse to occupy the same space, and why a beam of light is coherent. Bosons love to occupy the same space. It is the subtle, underlying bookkeeping that defines the physical laws of our everyday world, translating the deep structure of the quantum field into the tangible properties of chemistry and condensed matter. As we move toward the final stages of our exploration, we acknowledge that the universe is one of quiet, elegant constraints: the constraint of the uncertainty principle, the constraint of indistinguishability, and the consequent constraints of the exclusion principle. These rules of non-negotiable physics dictate the appearance of our stable, diverse, and knowable world. Our final philosophical question turns from the structure of the particles themselves to the ultimate question of the universe's ultimate fate. If the vacuum is not empty but a sea of activity, what does that quiet activity tell us about the ultimate closure of reality? We move toward the arc of the great silence. The quiet discomfort of the double-slit experiment and the absurdity of Schrödinger's cat were only the beginning of the revelations. These paradoxes hinted at a reality of simultaneous possibilities, but they were confined to single particles or single, sealed systems. Our journey now leads us to the most peculiar and deeply unsettling feature of quantum mechanics, a phenomenon that challenges the very notions of space, time, and independent existence: quantum entanglement. Imagine two tiny electrons born together in a single, high-energy interaction. For a brief moment, their wave functions intertwine, linking their fates forever. We then separate them, allowing one electron to travel away from its partner, perhaps across the vast gulf of the laboratory bench, or even to a great distance measured in miles or kilometers. According to the quantum rules of their birth, these two particles share a single, composite wave function, even when they are separated by what appears to be an impossible distance. Consider a property of these particles, such as their spin, which is a fundamental, quantized characteristic, an intrinsic form of angular momentum. Like the electron in the box, the spin of each particle remains in a state of superposition until it is measured. It is simultaneously spinning both up and down, a quantum coin flip that hasn't landed yet. However, because they are entangled, their spins are correlated in a perfect, inverse relationship. If particle A is measured to be spinning up, particle B must instantaneously be spinning down, and vice versa. This perfect correlation is the quiet tension that defines their shared existence. Now, picture the experimental scientist performing a measurement on particle A. The moment the measurement is performed, the wave function of particle A collapses from its dual state into a single, definite state, say, spin up. Because the two particles are linked by their composite wave function, particle B, miles or thousands of kilometers away, must instantaneously collapse into the opposite state, spin down. There is no time delay, no communication, no signal that travels between them. The information is transmitted across the space faster than the speed of light, an apparent violation of Einstein's cherished principle that nothing can travel faster than the speed of light. It was this seemingly impossible instantaneous connection that led Albert Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, to formulate a famous philosophical challenge in 1935. They argued that quantum mechanics must be an incomplete theory. If a measurement on particle A instantaneously determined the state of particle B without any physical signal traveling between them, then particle B must have possessed that definite spin state all along, stored as a quiet, hidden variable, a secret internal instruction which the quantum theory simply failed to account for. To Einstein, the idea that a measurement here could instantaneously influence a reality there, without a local cause, was simply spooky action at a distance. It violated the principle of local realism, the idea that objects have definite properties, regardless of whether we measure them, and that no influence can travel faster than light. For decades, this remained a philosophical standoff, a matter of quiet, conceptual debate, until the 1960s, when the brilliant physicist John Bell devised a mathematical theorem that could actually be tested. Bell's theorem is one of the most profound quiet achievements in the history of science, for it showed that the predictions of quantum mechanics were mathematically incompatible with the predictions of any theory based on local hidden variables. In essence, he created a clear, measurable difference between a world that is locally real and a world that is fundamentally spooky. The final experimental anomaly that broke the classical intuition came in the 1970s and 80s, with the groundbreaking work of experimental scientists like Alain Aspect. These precise experiments involved sending entangled pairs of photons to detectors separated by large distances, changing the measurement settings at the last possible nanosecond to prevent any possible light speed communication. The results, confirmed repeatedly by countless laboratories around the world, were a clear, quiet triumph for quantum mechanics. The correlations between the two distant particles consistently violated Bell's mathematical inequalities. The implications are stunning. You are forced to accept that either reality is not local, meaning an event here can instantaneously affect an event there, or reality is not real in the classical sense, meaning the particles did not possess a definite spin before the port. Measurement. Most physicists have quietly settled on the latter, realizing that the non-locality is only apparent. No actual information can be transmitted faster than light. Using this method, only correlations are instantly established. This entanglement is the universe's ultimate quiet secret, suggesting that the fundamental constituents of reality are not independently existing objects, but parts of a single, indivisible whole. Once they interact, they are forever linked. participating in a shared destiny that transcends the limitations of space and time. It is a profound, subtle echo of ancient philosophical traditions that speak of unity, of interconnectedness, where the separation we perceive is merely an illusion of scale. As you reflect on this strange connection, you notice how it challenges the very way you define an object. Is your hand a truly separate entity from the rest of the universe, or is it inextricably, quietly entangled with the particles that created it? The universe refuses to be neatly cut into separate pieces. The evidence deepens its strangeness, forcing us to consider that the deepest structure of reality may be relational, defined not by what things are individually, but by how they relate to everything else. To proceed further, we must now move from the evidence of strange behavior to the quiet, foundational uncertainty that underlies all of this. The principle that fundamentally limits what we can know about a quantum particle. This necessary limitation is a core piece of the universal design, and it leads us into the next phase of our quiet documentary. Our quiet journey into the deeper structure now encounters a phenomenon so utterly contradictory to the logic of the classical world that it seems like a subtle form of material impossibility: quantum tunneling. This is the act where a quantum particle, without ever expending the necessary energy, manages to pass clean through a solid barrier, like a ghostly presence slipping through a thick wall. Image illustrating quantum tunneling, showing a wave function decaying inside a potential energy barrier and reappearing on the other side. Imagine, for a moment, the wall of your own room. In the classical, shadow world of fixed facts, if you were to toss a small rubber ball at that wall, and the ball did not possess enough kinetic energy to break through, it would simply bounce back. The ball's certainty of location, its definite boundary, dictates that it must remain on one side of the barrier. The energy required to overcome the potential energy barrier of the wall is non-negotiable, a fixed toll that must be paid. However, in the underlying quantum reality, governed by the continuous flow of the wave function, the rules quietly change. Consider an electron, or a proton, encountering a potential barrier, a thin insulating layer, for instance, or the repulsive force that keeps atomic nuclei apart. The electron does not possess enough energy to surmount the barrier classically, yet the smooth mathematics of the Schrödinger equation offers a quiet, improbable escape route. When the electron's probability wave encounters the barrier, it does not instantly stop. Instead, a tiny part of the wave function, the mathematical description of the electron's potential presence, penetrates into the forbidden region. Within the barrier, the probability amplitude decays exponentially, becoming rapidly smaller the thicker the wall is. If the barrier is wide, the wave function quickly fades to zero, and the electron is guaranteed to be reflected. But if the barrier is sufficiently thin, the quiet, persistent tail of the wave function can extend all the way through the wall, emerging on the other side with a small, yet non-zero, amplitude. This small, surviving amplitude on the far side of the barrier means there is a finite, calculable probability, a subtle chance that the electron will suddenly, instantaneously, materialize on the other side of the wall, without ever having been in the wall in the classical sense, and without ever having possessed the energy to pass over it. It is as if the particle, in its state of superposition, quietly considered all the possibilities, realized that there was a tiny chance of appearing on the far side, and then, in the instant of commitment, chose that improbable outcome, the particle refuses to obey the classical laws of energy. The process is not one of drilling or boring. It is an act of pure, probabilistic transition. When the electron tunnels, it is exploiting the quiet permission granted by the uncertainty principle. For a fleetingly short time, the energy of the system can be uncertain enough for the electron to briefly exist in a non-classical state inside the wall. This phenomenon is not merely a theoretical curiosity. It is a critical and recurring feature of the deeper structure of reality, and it has profound, practical consequences that are felt even in the world of our sensory experience. For instance, without quantum tunneling, the sun would not shine. The temperatures and pressures in the core of the sun are not high enough to allow hydrogen nuclei, protons, to overcome the huge electrical repulsion that separates them and force them to fuse into helium. Only by quantum tunneling through the repulsive barrier can the protons quietly collide and initiate the nuclear fusion that powers our star and eventually all life on Earth. The very light that illuminates your room at this late hour is a product of an act of quantum impossibility occurring 93 million miles away. Closer to home, the quiet, subtle operation of the digital devices you may use every day depends upon this strange physics. Tunneling is the fundamental principle behind the scanning tunneling microscope, an instrument of almost unimaginable precision that allows us to image single atoms by exploiting the electrons that tunnel through the tiny vacuum gap between the probe tip and the sample surface. It is also a key mechanism in flash memory, the storage used in countless mobile phones and computers, where electrons must tunnel through an insulating barrier to be stored or released. The deep philosophical meaning of quantum tunneling is its affirmation of the probabilistic nature of the universe. The particle does not know how it got to the other side. It simply does so based on a calculable probability inherent in its wave function. It is a fundamental truth that defies the classical demand for a continuous trajectory and a definite, localized position at all times. The quiet, underlying tension of the universe is thus revealed to be one of perpetual, probabilistic escape. Even the strongest barriers are, in the quantum realm, merely a mathematical hill, not an impenetrable wall, and there is always a tiny, subtle chance for the wave function to leak through. This movement through impossibilities is an elegant and subtle mechanism that allows the universe to maintain its continuous flow, even when faced with the hard, definite boundaries of energy barriers. To fully appreciate the strange beauty of this probabilistic flow, we must now turn our attention from the spatial boundary of the wall to the temporal boundary of the atom itself. We must investigate the nature of time and decay, moving from the possibility of presence to the quiet, inevitable conclusion of probability in the context of one of nature's most perfect coin flips, radioactive decay. Having acknowledged the echoes of the past, we now move past the single, mysterious particle and delve into the quiet, fundamental arena where all these strange behaviors originate, the quantum field. This is the deeper structure of reality, the concept that transforms the universe from a space containing particles into a space entirely filled with dynamic, underlying fields. Image illustrating the concept of a quantum field, perhaps with ripples or excitations on a subtle surface. Imagine that every type of fundamental particle you have ever heard of, the electron, the photon, the quark, is not a tiny, discrete marble flying through empty space. Instead, imagine that the entire universe is pervaded, everywhere, by a corresponding, continuous, invisible field. There is an electron field, a quark field, a photon field, and so on. These fields are the true, foundational reality. Space is not empty. It is a plenum, quietly vibrating with potential energy. A particle, in this new, deeper structure, is merely a localized excitation, a ripple, or a tiny, quantized vibration in its respective field. An electron is a hump, a precise quantum of energy vibrating in the omnipresent electron field. A photon, a packet of light, is a ripple in the electromagnetic field. This concept, known as quantum field theory, or QFT, is the modern, powerful language that describes all fundamental physics, and it quietly restores a kind of continuity to the Heraclitean flux. The flow is not just of probability, but of the field itself. The implications of this fundamental reality are profound. If you look at what we once considered empty space, the vast gulf between the electron and the nucleus of an atom, or the dark vacuum of interstellar space, you realize that this space is, in fact, incredibly active. It is constantly roiling and churning with microscopic, instantaneous quantum activity, the quiet, subtle manifestation of the uncertainty principle. The Heisenberg uncertainty principle does not just apply to a particle's position and momentum, it also applies to another complementary pair, energy and time. This means that for a fleetingly short period of time, the amount of energy in a tiny volume of space can be momentarily uncertain. This uncertainty allows for the spontaneous, instantaneous materialization of what physicists call virtual particles. These are particles that exist for such a minuscule, immeasurable fraction of a second, a time period so brief that the particle refuses to make eye contact with our most sensitive detectors, that they do not violate the fundamental law of energy conservation. Picture the vacuum now, not as stillness, but as a vast, quiet sea of activity. Pairs of virtual particles and antiparticles, say, a virtual electron and a virtual positron, spontaneously erupt into existence from the energy of the field, separate for an instant, and then just as instantaneously annihilate one another, returning the borrowed energy to the vacuum. This constant, furious, subtle dance is happening everywhere, all the time, beneath the calm surface of perceived reality. This concept of virtual particles, of the vacuum being a dynamic, bubbling broth of potential, provides the physical mechanism for all fundamental forces. When two real electrons interact, they do not simply touch or hook together in the Democritean sense. Instead, they exchange virtual photons, which are the quanta of the electromagnetic field. One electron emits a virtual photon, which is then absorbed by the other electron. This exchange of the virtual particle mediates the force, creating the repulsion that keeps the two electrons apart. The strong nuclear force, which holds the nucleus together, is mediated by the exchange of virtual gluons. The field is the quiet architect of force. The particles are just the points where the field's energy has localized. This realization completely reframes the nature of both matter and force, unifying them into the single concept of field excitation. We see that the non-local correlation of entanglement is simply the shared, indivisible nature of the field itself, the background substrate refusing to be cut into separate pieces. The concept of the quantum field also introduces a new kind of subtle, dry humor. The universe is constantly trying to borrow energy from nothing, only to have to pay it back instantly, like a tireless, silent financier operating at the most minuscule scale of time. This quantum foam is the source of a tiny, measurable energy known as the Casimir effect, another experimental anomaly where two perfectly uncharged parallel metal plates, placed incredibly close together in a vacuum, are quietly pushed toward each other by the imbalance of virtual particles outside the gap versus those that can fit in the smaller gap between them. This quiet, measurable force is direct evidence of the field's subtle activity, the vacuum pressure of the cosmos. As we conclude this exploration of the deep structure, we realize that the universe, at its core, is a vast, interconnected web of energy fields, perpetually in flux, governed by a beautiful, precise mathematical language. The solidity we perceive is an illusion of scale, merely the macroscopic average of countless, simultaneous virtual eruptions and annihilations. We have moved from the single hesitant particle to the universal field. This expansive view now necessitates a turn back to the human scale, asking the quiet, final question: how does this profound structure, this sea of potentiality and chance, reflect back on the mind that observes it? We move into the arc of the human reflection, asking about the nature of perception and consciousness in a fundamentally probabilistic universe. Our quiet, 3-hour journey through the secrets of quantum physics has led us from the initial shock of the electron's hesitation to the ultimate, continuous texture of the quantum fields that constitute the deepest structure of reality. We began with the definite, tangible world of classical intuition and end with the realization that all existence is an emergent phenomenon, a symphony of probability pools, a constant, irreversible process of decoherence, and a continuous dance between potential and actuality. Our final segment is a quiet, contemplative reflection on the meaning of this entire pursuit, focusing on the enduring human qualities, curiosity, humility, and awe that drove us to discover these profound secrets. The first quiet reflection is on the nature of humility in the face of uncertainty. The quantum world, by replacing the deterministic certainty of classical physics with irreducible probability, forced a deep intellectual humility upon humanity. We learned that there is a fundamental, mathematical boundary to our knowledge, the uncertainty principle that cannot be crossed, not because of clumsy instruments, but because of the nature of reality itself. The universe quietly insisted that the observer and the observed are not separate, and that to define one aspect of reality is to fundamentally blur another. This is the enduring lesson of the double-slit experiment. The universe refuses to be fully pinned down by the definitive language of classical objects. The physicist, the scientist, is no longer the detached, objective viewer, but a quiet participant in the final definition of reality, an inherent part of the experiment. This enforced humility is, ironically, the source of immense power, for the quiet acceptance of chance allowed us to find the deeper, more powerful mathematical elegance of the underlying fields. The second quiet reflection concerns the persistence of awe in the face of complexity. We discovered that the entire vast three-dimensional cosmos, with its superclusters of galaxies, is merely the large-scale manifestation of the random, infinitesimal jitter of the quantum vacuum, a quiet triumph of the uncertainty principle. The massive structures of the universe are the grandchildren of pure quantum chance, amplified and solidified by the rapid expansion of inflation. The beauty of this realization is that the elegant architecture of the cosmos is woven from the same fundamental principles that govern the single electron, a profound, non-local unity that links the smallest to the largest in a continuous, consistent, mathematical tapestry. To find that the laws governing the infinitesimal are also the laws governing the infinite inspires a kind of gentle, philosophical wonder, a quiet confirmation that the universe is not just complex, but fundamentally coherent. The third, and perhaps most important, reflection is on the nature of curiosity and the quiet, continuous search for the fundamental truth. The entire edifice of quantum mechanics, with its paradoxes and philosophical ambiguities, was built not to create technology, but to resolve a series of quiet, persistent experimental anomalies that defied classical logic: the blackbody radiation, the photoelectric effect, and the strange behavior of the electron. It took decades of painstaking, quiet work in laboratories, sometimes across continents, to confirm the non-local reality of entanglement and the physical consequences of the zero-point energy. The enduring human drive is the need to know the hidden structure, to peel back the layers of the phenomenal world and understand the subtle, persistent mechanism that generates our definite reality from a fluid ocean of potential. The final synthesis is the understanding that the universe is fundamentally an informational structure. The quantum wave function is a map of possibility. Measurement and decoherence are acts of information transfer, and the definite, classical world we experience is the stable, emergent result of this relentless processing. Our very consciousness, the subjective experience of a single, definite reality, is a highly decoherent informational system, a quiet product of the universal process of turning potential into actuality. The secrets of quantum physics, in the end, are not just about the behavior of small particles. They are about the deep, quiet relationship between knowledge, certainty, and existence itself. The paradoxes remain, notably the unresolved conflict between the smooth geometry of general relativity and the jittering chaos of the quantum fields, a grand theoretical question that waits for a future, quiet genius. The measurement problem, while partially explained by decoherence, still carries the heavy, quiet question of how the subjective experience of reality emerges from a purely mathematical description. But these enduring mysteries are not a failure of physics. They are the signposts for the next stage of the journey, the quiet invitation to the next generation of thinkers. The quiet pursuit of these secrets is the most profound expression of the human desire to understand our place in a universe that is both elegant in its mathematical structure and profoundly strange in its operation. We have traveled far, deep inside the texture of reality, and we leave this quiet journey with a gentle, profound sense that the world we see is only the surface of a far more beautiful, subtle, and fundamentally uncertain truth. As we gently pull back from the Planck scale and return to the quiet hours of your own space, let the echoes of this journey settle, the persistent hum of the zero-point energy, the subtle geometry of probability, and the realization that the cosmos is a vast, continuous negotiation between fluidity and definition. We have traced the human path from the certainty of the clockwork universe to the elegance of quantum chance. It is a path marked by quiet perseverance, where paradox is embraced as the key to deeper truth. We honor the enduring curiosity that insists on asking the hardest questions. the same quiet impulse that leads us to seek structure in the stars and stillness in the night. The secrets of quantum physics remind us that the world is more beautiful and subtle than our intuition allows, a place where all things are subtly connected, even across vast distances. The light you are resting in is the same light that traveled through a million possibilities before settling on this single, definite moment. Rest well within the knowledge that your own existence is a triumph of immense, beautiful probability, a quiet piece of the cosmic structure. The fields persist, the energy flows, and the grand, unified wave function of the universe continues its quiet, eternal evolution. You are still a part of the greater system, ready to begin the next cycle when you awaken.